I'm Antonio Sala, and in this video we'll discuss some examples on regression with the Matérn kernel. In fact, in this first video we will only discuss the problem and example setup and basic ideas on the first order spectral factor noise filter associated to some parameters of said kernel. Let's go. First, we will show for a split second the Gaussian kernel regression code. We'll have a covariance kernel to be later defined, and we need a function to obtain the covariance matrix for all pairs of points in vectors x1 and x2, and with this covariance matrix we can apply Gaussian process regression using this code, in which x1 are the points in which I wish to do the regression. This will be the prior. My prior mean in this example will be 0. We'll encode it later on. Prior mean and prior variance. And if we have some data, the posterior is computed with this code in here. As we discussed the meaning of this in other videos, you can just pause and inspect the code yourself or watch the said videos. See the links in the description. With this code, we'll do Gaussian process regression in this kernel we are going to define now. We are testing the Matérn covariance kernel with this formula, and we'll implement it in MATLAB as follows. We'll have some parameters. The first one will be the order of the spectral factor, because as I am a control people, I like to think in filter transfer functions, and then I will start with a first order filter. Rho will be a distance parameter proportional to the filter time constant, tau, and this will be the standard deviation when this filter reaches a stationary regime, and this SGMED will be later on used to indicate that the mean of the data may not be 0, and we expect the mean of the data to be in my prior normally distributed with a standard deviation of 2. So the Matérn kernel we'll see here will have 0 mean, but we think that there is a 95% likelihood that the actual mean of my data is between plus minus 4. Of course, these two parameters need not be equal, but okay, we just invented them. Good. The new parameter of the Matérn kernel is subtracting 1/2 in this one-dimensional setup, and well, this is the formula for the Matérn kernel, which is a long one. Here we have it, in which we have the Bessel function and the gamma function, which appear in this covariance definition. And well, instead of d for distance parameter, I call it x, but it's just the same. It must be a positive argument. And in this case, we get this exponential kernel. More complicated functions will appear when we change the order of the spectral factor. And well, if we wish to know the power spectral density, then we must take the Fourier transform of this symbolic Matérn expression, but okay, replacing x with absolute value of x because it must be symmetric in the abscissa axis, and then, well, carrying out the Fourier transform and simplifications, we get this power spectral density associated to this spectral factor, which is the filter we would pass a white noise through to get the Gaussian process we are discussing. Indeed, the modulus of the frequency response squared, you can check that it results in this power spectral density, so we can go on. The next thing we are going to do is compile it from a symbolic toolbox object to an ordinary MATLAB function in which you get numbers in, numbers out. I use MATLAB function to carry out that task, so this is a numerical function, and then my covariance kernel will be this Matérn numerical stuff. But okay, we have some kind of modifications. First one, the argument in a stationary covariance kernel must be the distance between the samples x2 minus x1 norm. But in some cases of the parameters, there are some limits of the Bessel functions, etc., that can be carried out symbolically, but numerically MATLAB gets a bit lost. So to avoid some errors in later executions, if the norm is very close to 0, then I will just replace by 10 to the minus 12 the argument to this Matérn stuff. Of course, in here I would have no errors, just an exponential, but in other cases with the Bessel functions and whatever, this avoids some problems, and conceptually it's just 0, okay? Then this part, which is the numeric MATLAB way of doing this here, this would be the non-parametric kernel component, this Gaussian process we would interpolate, and then we will add this constant. This is 2, so we are adding 4 to the covariance. This means, as explained in other materials, that part of the variance of a sample is associated to a unknown constant parameter, a constant non-zero mean, let's say, which is common for all the samples. So base mean level uncertainty is encoded with this addition of this constant. Then, once we have this kernel, we can study the prior and the posterior once we load it with some data. So we'll test stuff in this grid between -2 and 4, and for instance, with this plotting code, I can plot this kernel autocovariance, and we see that the exponential decays up to the base value of 4, which is the constant mean uncertainty variance affecting all samples independently of their distance. So this is the autocovariance, and we can predict with empty data the prior. With this line we'll get confidence intervals, and with this multivariable normal random I can throw the dice and obtain realizations of my Gaussian process. And then that realizations have this shape. These shapes are very noisy, but okay, that's expected because we are filtering a noise by just a first order filter, so a lot of high frequency content gets through the filter, and we see it here, and also filter bandwidth is quite large, the pole is fast, and say, apart from the mean level, samples separated distance of 1.5 or less have very low correlation in this noisy Matérn component. But, well, that's what we have set as prior. If we see trials instead of 15, just a couple of them each time, then here we have a couple of realizations in which, well, it seems that the mean of the first one is around -2, but the mean of the second one in green is around +2. Here we have another 2 realizations. The overall of them is zero mean, but each one is non-zero mean. Here we have, and more of them. So, well, this is our prior. Then we are going to do Gaussian process regression, assuming that we are going to acquire samples from one of these realizations, say here and here, and we need to interpolate and extrapolate in mean and variance what could have happened in the non-sampled test points. So let's go. I have here a collection of samples, and well, to start easy, we'll start by just loading one sample and computing my posterior. So I have my prior confidence bounds in red and my sample is in there. So what is the posterior? We use this predict GP code, and this is the posterior. This is the sample, so everything passes through the sample. Measurement noise is very small. And then the mean is a sort of exponential decay to a mean value that is, I sampled 2.2, and then as my Matérn kernel has the same standard deviation as my constant mean, then it splits into the deviation, and then roughly it apportions half of it, 1.1, to the expected mean, and another 1.1 to the increment due to the non-parametric exponential kernel stuff. So, well, we get this. But of course, as my realizations are very noisy, we get this exponential decay to the mean just in expected value. A lot of noise accumulates, so my confidence interval, once I get farther away in distance, that to 1.5, let's say, then okay, the amplitude of the uncertainty is equally to the, let's say, open loop, no data, prior estimates. So this is how we update and interpret the posterior with just 1 point. Of course, if I had a lot of uncertainty in the constant mean, 20, then my posterior would apportion all the deviation from 0, the prior mean, to that constant parameter, and vice versa. If my non-parametric component had a lot of variance, then everything would be apportioned to it and the exponential decay would decay to 0. But okay, how do we split the observations in change the mean, change the Matérn kernel Gaussian process? Depends on the prior. If we go back to 2 and 2, we'll now discuss what it means inputting 2 samples, ending here. These are the 2 samples, and we see that it stitches them, at least in mean, with fragments of exponential curves, let's say. And well, if my prior is very noisy, confidence intervals get very wide at a short distance from the samples. If I now zoom in and I reduce the distance parameter to 0.1, we see that basically the blue line, the expected value, is sort of an exponential bump into a flat horizontal line, and the width of that bound depends on the correlation distance. In here, the bumps do not overlap. With higher correlation distance, bumps overlap, and if we increase the correlation distance to 80, let's say, then the pole of the spectral factor tends to 0. It approaches an integrator. The exponential is very slow, and the exponentials overlap, forming sort of straight line. Indeed, if we compute the derivative of this, we see that the resulting interpolation has piecewise constant derivative, which means that the Gaussian process produces a piecewise linear interpolation. If I add more data, 6 points in here, then with this very large time constant, spectral factor pole close to 0, pure integrator, then in the limit case, exponentials are no exponentials, but straight lines. And we get, again, piecewise constant derivative, indicating a linear interpolation between samples. Of course, if the distance parameter decreases, then the interpolation between points again resembles a superposition of exponentials, let's say. So we'll conclude here. In this video, we have seen the Gaussian process regression problem statement and how to do it with Matérn kernel formula, but we have just stuck to the first order noise filter equivalent case, let's say, and then we have seen that the expected value, blue line, of the interpolation and extrapolation are pieces of exponentials around an estimated mean value whose uncertainty we included in the kernel, and if the time constant distance parameter was very long, spectral factor was approaching an integrator, and then the result was linear interpolation between the samples. In a forthcoming video, we'll do some tests with higher order spectral factor filters and even fractional order, but for brevity, we'll finish this video now here. Thanks for watching.